So once we've determined that the mass of an electron is pretty small compared to the overall mass value of an atom, the first model in which we come up to describe the model, or describe the atom, is the bread pudding model. The idea of the bread pudding model is that we have an atom, okay? And inside that atom we have chunks. We have a light that's striking me. Yeah, looks like it's the top light. So inside there I have chunks of negative charge. And if we can exert enough voltage, enough electrostatic pressure, I can force those chunks out of that atom. That was the original model of it. Well, they believe that these particles, these chunks, are suspended in a sort of fluid that was positively charged. Okay? So the more negative charges I have in here, the bigger this atom gets. The more fluid that's positively charged, the more positive charge I have. Okay? So we have these chunks of negative charge that we call electrons being suspended in a fluid that we consider to be positively charged. So that's what we believe the model of the atom was. Okay? So we proposed an experiment. We said, all right, we'll take this model and we'll say that if this model is true, okay, and I create an oven that bakes off alpha particles, and if you remember what an alpha particle is, positive, positive, and then two neutrons. So let me make that alpha particle a little bit bigger. So that it's two neutrons, two protons being fired at it, basically a helium particle. It's being fired at this atom. Okay. Now the atom of choice that we picked for this experiment was a gold atom. Pretty big. Okay. A pretty big atom. It's got enough charge, and it's also pretty malleable. So what we did is we took a nice big flat sheet of gold. We pounded it out as thin as we possibly can. As thin as we possibly can. And we had a series of these atoms all up and down, and we fired these alpha particles into that gold foil. Okay? So we believe, because they were positively charged, entering a slightly positively charged fluid, that more than likely we were going to experience a small deflection every time we went through there. Okay? Not only the positive charge, but the chunks of negative charges. And so as this alpha particle, a very massive particle, comes to this sheet of gold, it'll fly through, but every time it flies through, it's a illusion. Okay? So that'll calculate the positive charge. Cool? Didn't happen that way. As a matter of fact, how it did happen, and I'm going to draw it over here on the small section that I've got available, is that when we fired alpha particles through that sheet of gold, so here's my sheet of gold, and here are my incoming alpha particles, most flew through. Okay? Just went right on through. Cool? Some were deflected. And even fewer were majorly deflected, to the point where it pushed it back in the opposite direction. Okay? So most of the particles flew right through with no deflection. A few of them experienced a minor deflection, and even fewer experienced a major deflection. Okay? So that proves that this model of what we thought the atom was is wrong. Okay? Because if it was to fly through that positively charged material, you're going to experience a deflection every time. What we experience is the exact opposite. We experience a deflection very rarely. Okay? So because of this experiment, because of this and our probabilities, if I fire 1,000 through them and only deflected, then we have this positively charged goo that we thought was there of the original volume. Okay? So we have this image of an atom, and if only 1 out of 1,000 gets deflected, that means that the center, the nucleus, what we know now as the nucleus, the center of positive charge, is only 1/1000th of its original, of the volume of that atom. So you could fire as many as you want, and you could get a better and better idea what the volume was of that chunk of positive charge. So because of this experiment, we throw out an old model, and we come up with a new model that determines the approximate size of the nucleus of a gold atom. Okay?